All right, it's 11 a.m., so let's start. Please finish your conversations, or you can actually continue your conversations just in the way I don't hear you. Yeah. So today we're gonna start new topic, as you can see. It's linear momentum of particles. I believe that Professor Sunny talked about it yesterday. Yes. And then we will do 3 examples. Example number 1, 2, and 3. Okay, so something's happening with my laptop, and that line will stay here forever, apparently. Okay, example number 1, 2, and 3. Yeah, and before we do brief lecture review, let's see where are we on our timeline. Aha, we just finished three topics, yes? Kinematics, kinetics, and work energy, yeah? But they might be coming back all the time, okay? Anyway, I just want to say that we just started this topic. Questions? Then brief lecture review, very brief, okay? So what I would like to talk about? Are you kidding me? It will stay here forever? I don't believe in that. It will. Okay, we will live with that, guys. Okay, I don't have time to fix it. Anyway, ignore that red line. Okay. So what do we have? Aha, we have our old good friend particle P following along this trajectory. Yep. And what else do we know? Aha, our particle P has mass m, and our net force F is acting on our particle. So we know that this is true, yes? F equals to ma. And before, when we were talking about work energy method, we just took integral of this expression over path. Do you remember? Yeah. So we first of all we projected our vectors on the path. Then we used this definition of acceleration, and after a couple of algebraic steps, we ended up with this expression. Okay? That you should all know very well right now. Today, on the other hand, we will just start exactly the same with f equals to ma, but this time we will do integral over time. Okay? So we will use this expression for acceleration. Let me plug it back in here. Okay? So we will, if you do that, you will end up with f dt equals to m dv. All right? And let's integrate from time instant 1 to time instant 2. Time instant 1 to time instant 2. And of course, that time instant 1 corresponds to point A. And time instant 2 corresponds to point B. T2, I mean. Okay. So the integral on the left-hand side is just an impulse. And this integral, if we solve it, we will end up with mv at time instant 2 minus mv at time instant 1. Okay, so we can simply write that mv1 plus the impulse is equal to mv2. And we will use this expression today like 3 times or more. Okay, so in other words, initial momentum plus impulse results in final momentum of our particle. Questions? I don't hear any questions. So let's start example number 1. I hope we can. Please ignore that red line and familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have our car that we will model as a particle. We know that our car starts from rest, and it needs only 4.2 seconds to reach speed 62 miles per hour. We know that the force propelling the car is given to us with this in this expression, and they ask us to find F0. F0 that is needed so that everything else in the problem statement is true. So this is how I solve these problems. I start with momentum diagrams. Diagrams or diagram, let's say diagram. So I would like to draw the situation that happens at instant t0. I would like to also draw what happens when time ranges from t0 to t final. And I also would like to draw what happens at t final equals to 4.2 seconds. Okay, we will model our car as a particle, but I will represent it as a rectangle. So there will be a rectangle here, rectangle here, and rectangle here. Okay, we are told that our particle starts from rest. So we have mv0, this is equal to 0. We know that our car at the end will have some velocity. So we'll have here mv final. And in the middle diagram, I would like to show all the forces acting on our structure. So I know that mg acts this way. I know that normal force acts this way. And there is also that force F given as a function of t acting on our system. Are there any other forces? No more forces, yeah. So let's not forget also about our integral, okay? But because initial momentum at the beginning plus impulse results in final momentum, okay? Any question to that momentum diagram? I think it's quite clear what each of these drawings represent. Yep. So if is that clear? Any questions? Yeah. So once we have momentum diagram, we can write momentum equations. Okay, but only in the x direction. In the x direction. Okay, and this is our positive direction. Let's assume that this is our positive direction. So we will have mv0 plus integral from sometimes 0 to t final of f of t, because this is the only force acting in the horizontal direction, and it will result in mvf. Okay, let's plug in values. So this guy will be 0. This will be integral from 0 to 4.2 f0 1 minus e to the power of minus t divided by tau dt, and this is equal to mvf. Okay, I believe that f0 is constant, so we can just place it in front of the integral, yes. And if I remember correctly from school, that integral has following solution. F0 t minus tau, I think, yeah, plus tau from 0 to 4.2, and this is equal to MVF. Okay, so our F0 can be multiplied by 4.2 plus 0.5 e minus 4.2 divided by 0.5 minus 0 minus 0.5. And this is equal to 3850 divided by 32.2 times 90.9333. If you grab your calculators, you will see that this expression is approximately 3.700, and this expression is approximately 10872.460. All right, our F0 is triumphantly approximately 2938.503 pounds. And this is the answer. Questions? Vincent?
The race car was 3,800 pounds. Just like mass and weight, like for force, shouldn't we want the mass times the acceleration due to gravity? Basically, I'm asking why in the last equation.
Yeah, but we're in US units. Yeah. So if they say that something weights in US units, that means that mg is equal to that weight.
Oh.
Anybody else? If not, that was easy problem. Yeah, that was very easy. Yeah. Let's look at something more interesting. Okay. Example number 2. That was just to warm you up. As usually, please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? We have two bodies this time, right? We have ramp, which weighs big M, and crate that has mass of small m. Okay, system starts from rest, and we know that this angle is 30 degrees. We also know that there is no friction in the system. Yes, zero friction, and we'll use that information within like 10 minutes. Okay, and how do we know that there is no friction? Because they told us that the surface of the ramp is smooth. Okay, so that even that red line is underlying that, so it was even useful in that case. Yeah. Okay, and they told us to figure out the velocity of ramp and crate once the crate is here, is at the end of the ramp. Okay, let's do it. Any questions to the problem statement? Any questions about the problem statement? That's correct in English. Yeah. Okay, so solution, momentum diagrams. We're gonna follow exactly the same steps as previously. Momentum diagram. So I would like to know what happens at time instant t0. Please observe that they didn't tell us how much time that motion takes. I don't know what is t0. I don't know what is tf. I don't know. So anyway, I also would like to know what happens in between T0 and Tf. And I also would like to know what happens when T is equal to T final. Okay. Let's see if we are able to figure that out. Yeah. It's a rhetorical question. Of course, we know how to do it. So I wanna draw a ramp here, and I'm going to copy it here and here. So at time instant 1, at time instant 0, our crate is here, right? And at time instant final, our crate will be here. So you guys can clearly see that that ramp traveled this distance, that 3.5 meters, yes? I'm gonna call it S. And we know that this die has mass little m, this die has mass big M, and we also know that mv0, or let's do it maybe mvc0, okay? C standing for crate, and R will stand for ramp. Okay, so this is 0, and also big M v ramp 0 is also 0. Yeah, they just start from rest. However, at the end, they have some velocity. Yeah, ramp will for sure go this way. I have no doubts about it. I don't know, VR, V ramp. Yeah, and crate will go with the ramp, but also it will go relatively to the ramp. Do you see that? Our crate will have for sure this component, mvr, but it will also have this component, mv crate relative to ramp. I hope that you guys can see it. So the actual velocity of that ramp will be pointing in this direction. And I bet guys that you know how to add vectors. Yeah, I apologize that we spent time on that. Wait a second, maybe I will just move this one first. So the actual velocity of that crate will be here. V crate. Okay, let me give me like 10 seconds, okay? Because I do not like that we ended up with right angle there, okay? So I'm just gonna have this vector a little bit longer, okay? We're gonna have this vector a little bit longer, okay? So actually our VC will be pointing this way. I just didn't want you to think that this is like a right angle or something, yeah? Okay, so we are done with our momentum equation, yeah? Sorry, when it comes to our momentums at the beginning and at the end. Let's see what forces act on our system. So I would like to place my crate here because it is sliding clearly. And I think that these are the only forces acting on the system. We have mg, and we have some normal force. Are there any other forces acting on our system? Yes, Trevor?
The normal force between the frame and
These are internal forces. Yes, this is an perfect. Yes, this is, but don't draw it. Don't draw it. Yes, we have internal forces here, but I do not treat each body separately right now. I just treat the entire system. Okay, so I'm gonna hide these forces there. I don't care about them. Yes.
And that would be energy is not necessarily considered for momentum. Like that's why you don't draw it.
To draw these forces?
Yeah.
No. The correct answer is that I look at the system as a whole. Yeah, I look at the entire system. I do not look at each body separately. If you want, AJ, you can solve that problem at home. I did it when I was looking at each body separately. Yeah. Then you must include them. Yeah. In here, we just check this out. We just look at two bodies at the same time. Yeah. So there are no other forces acting on our system, right? No other forces. So let's not forget about our integral. So it will be integral from t0 to t final dt. Okay. So now momentum diagram. Momentum equations, yes? But before we write them, I have a question to you guys. Let's have a digression here, And let's look at this. It's not a free body diagram. It's like a free system diagram, yes? It's not free body diagram, it's free system diagram, yes? Is that n, who thinks that n is equal to mg plus mg? Is this true? Yeah? And who think that it is not true? Spoilers, if you say that it's not true, I will ask you why. So be ready for that. Anybody want to tell me why this is not true? Because it is not true in this case. This is not true. And I would like somebody to tell me why. And that person will be Calvin? No, Colin. Yeah.
Is it because the crate is moving?
It is because the crate has acceleration. Yes. So you earned the Snickers. I will buy you Snickers next time, okay? This is my favorite candy, okay? Do you like Snickers? Yeah, okay. Okay. I solved it at home. I solved it for two bodies separately, okay? And I figured out that n is actually, in this case, n is equal to mg plus cosine squared theta m plus sine squared theta. I think I forgot about g here, yes? G here also. So n is actually equal to that expression. And if you use your skills you learned in kinetics, in the kinetics chapter, you should be able to obtain that. Just a digression. Okay, let's go back to our equation. So let's write our momentum equations. Question to you: is there any force acting in the horizontal direction? So look at that free system diagram. Do we have any forces acting in this direction? In the horizontal one? No. What does it mean? That momentum is preserved in the x direction. There are no forces acting in the x direction. We have momentum preserved. Let's write it down. No forces acting in the horizontal direction. That implies that momentum preserved in the x direction. Okay, so we will write our momentum in the x direction, and let's say that this is positive direction. Which one? Which I want positive? This one I want positive. Okay. So we will have m v crate 0 plus big M v ramp 0 plus 0, yeah, plus 0 impulse, so let's not even write it. And this is equal to negative M MVR, negative M VR, and we must do projection here, yes? So let's do it quickly. So this will be here, and I need this component. Oh, I need this black component of green vector. So I think that 30 is here, so 30 will be here. So this component will be M VCR cosine 30 degrees. Yes. Even though I have a mistake in my notes, this is true. Okay, so we will have in here plus MVCR cosine 30 degrees. Okay, guys, and I believe that this was 0 and 0, yes? This is 0, and this is 0. So we can write that 0 is equal to this expression. Okay, so how many equations do we have? We have one equation and two unknowns. Because this is unknown and this is unknown. Dang, not good. Not solvable, yeah. Okay, guys, any questions to what happened so far? Yeah. If not, I need your help. We need one more equation. How to find it? Where is it? Anybody want to help me? Yeah. Okay, Trevor, let's go for it. Yeah. Okay, you mean vector, and of course vector-wise, yes? We will use it later, okay? It's not exactly what I'm looking for because, look, we don't know this vector. Yeah, yeah. It is unknown. By the way, they ask us to find it. Check this out. Yeah. But okay, but we will use your idea in a second, okay? Okay. And your name is Lars.
Would you find the CR from the mass times gravity, or like that in the direction?
You mean in here, this direction? Not really. So there are two options actually. Yeah, and you want to say something, Brian? That's a good idea, but bad idea also at the same time. You see? Do you know why? And I was actually waiting for somebody to make that mistake because we don't know n. So once you know n, it's easy to find it, yeah? But you first must find that monster. Okay? So I would like to avoid, I actually would like to, that problem can be solved without finding that n. And I would like to avoid it. I don't want to solve for n. But guys, here is some information. There's no friction in the system. So what we should go for? Yeah, energy is preserved. There is no dissipation, exactly. So we are not going to go for the y direction. We could, but I do not recommend. Let's just look at the energy equation, okay? Energy, there is no dissipation. There is no dissipation in our system. Energy is preserved. Okay, so let's do our routine. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And AJ said that this is 0. And he's right. So we have to find these 4 guys, not 5, but 4. Okay, system starts from rest. This is 0. Potential kinetic energy at the end. So I think that we have 1/2 of big guy VR squared plus 1/2 of little guy V crate square. Yeah. Okay, potential energies. Let's put a datum in our system, okay? So I want to put datum here. Okay, so at the end, our crate is here, yeah? Our crate is aligned with the datum. And at the, so potential energy will be 0. So here we can put 0. And at the beginning, our crate is like that much above. Is that much above the datum, yes? This distance. And this will be, if 30 is in here, S times sine theta, sine 30. I believe so. Okay, so this is our elevation at the beginning. mg S times sine theta. Perfect. Let's plug in everything back into our equation, and we'll end up with mgs times sine theta, and this is equal to 1/2 mvr squared plus 1/2 mvc squared. Okay, so we introduced a new, so we have our equation. We have our equation, yes? However, we introduced a new unknown in here. Yeah, VC. And now I would like to give back mic to Trevor. Trevor, how we can get rid of this new variable? Exactly. We're gonna do here. So now, guys, we are going to look at this. Oops. Interesting. So now a question to you: do you remember the law of cosines? You do. 30 degrees is in here, by the way. Yeah, 30 degrees is in here. That means that 30 is in here. That means that if I remember correctly, our VC squared will be equal to VR squared plus, okay, you can get rid of these m's. Yeah. Plus V relative squared minus 2 VR V relative cosine 30 degrees. Okay, thank you guys. So now just let's plug back this in here, and we have 2 equations and 2 unknowns. Exactly. So I'm gonna steal this equation, if it allows me. Why you are not listening to me today? Come on. Oh, great. I'm gonna steal this equation here, and I'm just going to replace this VC squared with what we just obtained. So it will be VR squared plus 1/2 of little m V relative squared minus m VR V relative cosine 30 degrees. Great, we have 2 equations and 2 unknowns. And they are VR and VCR. Okay, and I bet you know how to solve 2 equations and 2 unknowns. So let's just plug in values and solve for VR, VCR, And now, once we know these two values, we can also solve for VC using that law of cosines. Okay. So I did it yesterday at home. And I obtained that VR is approximately 1.004 meters per second. VCR is approximately 6.353 meters per second. And VC is approximately 5.482 meters per second. And these are the answers. This one and this one. Yeah, let's see if that makes sense. Let me copy this drawing here. And this guy is this one is 1.4. This red vector is approximately 5.482, and this guy is approximately 6.353. That makes sense because that green guy must be the longest, yes, in that triangle. That makes sense. Okay. Wow. Questions? Okay, so just keep in mind that even though we are in momentum chapter, we can still use some help of our friends from the previous chapters. Yes, so work energy can be useful, kinetics can be useful, and so on.
I just have one question about the so you're saying that so you're saying that n is not equal to mg plus mg, but any movement in the x direction, wouldn't that, since it's like perpendicular to the y, wouldn't that like not affect whatever's going on with the y?
No, because mg is going is accelerating downwards. So for the system, so that n, so that will affect that normal force acting in between bodies as well. Okay. Yeah, and that normal force will also cause increase of value of that force. Yeah. What can I say? Can I have an example from life? Yeah. Anyway, you must trust me, or you must solve it at home. Solve it using. If you solve that problem using kinetics, which is possible because I did it, you will end up with such expression, and you don't have to like believe me in anything I say. Then you will know it for sure. Okay, example number 3, or I can squeeze in one question or two right now. How do you like this example, guys? I think it's interesting, yeah? And this is actually what we are learning here, yes? Because some of you had a gut feeling that this will be true, for example, yes? However, dynamics tells us that it's not true, yeah? Also, I forgot to mention something when it comes to brief lecture review. Momentum is a vector, yes? So in here, we can distinguish between momentum acting in the x direction and y direction, yes? Energy, on the other hand, is scalar, yes. He falls asleep. Oh, no, okay. Okay, I wanted to say that if that happens, then we will finish our discussion, and then after discussion, nobody makes a sound. We leave, and we leave that person here. Okay? No, go to sleep, it's fine. Just don't snore. Yeah. Yes, and there was a question?
One quick follow-up question. So let's say hypothetically it's not slanted, it's just flat. In that case, n would be.
In that case, yes.
Okay.
Yes. Yeah. Okay. I don't have time to for more questions. So please familiarize yourself with the problem statement of example number 3 before we start our solution. All right. So what do we have in here? we have again two bodies, okay? Big body of mass uppercase M and small body of mass lowercase m. There is no friction in the system, and system starts from rest. And before we reach to our, so they ask us to determine the speed of the box at the instant it stops sliding on the cart. We will get there, okay? We will get there, okay? Before we get to this part of the problem and the other part of the problem, we must solve the hidden problem part one, okay? So work energy method, yeah? So what I want to do, I just would like to figure out what velocity will this body have when it's here, okay? I want to solve for V star. Okay, right before it enters the cart, okay? So I'm gonna do work energy method. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. And let's find these five guys. Actually 4, because we know that energy is preserved. So this is 0. No friction in the system. Okay, system starts from rest. This is 0. System at the end has some velocity. 1/2 big M V star squared. How about potential energies? I forgot about one potential energy. So I want to put my datum here. Here's my datum. So I think that at the end, potential energy will be 0, and at the beginning, it will be mg times 15. Okay, let's see what we obtained here. We ended up with mg 15 is equal to 1/2 mv star squared. So that means that v star is equal to 2g times 15. Plug in values, you will obtain that this is square root of 966. And V star is approximately 31.0805. Yeah, maybe I was thinking of solving that problem before coming here, because you guys should be able to solve such simple system in the middle of the night, yes, when somebody wakes you up, yeah. Okay, but anyway, we figure out what is V star. We figure out what is V star. Now we can start talking about momentum. Determine the speed of the box at the instant it stops sliding on the cart. Okay, let's draw our momentum diagrams. So I want to have that, I want to see what happens at time instant, let's say 0. I want to know, so it's pre-impact. I also would like to know what happens pre-impact. Maybe not. Okay, that's a bad idea. That's not true. So time instant 0, okay. I want to see what happens in this time range from 0 to t final. I don't know what is t final. I also want to see what happens at t equals to t final. Okay, so we will always have our cart. So I'm going to copy it. I'm going to copy it from here. I'm going to copy it here and here. So at the beginning, we have our particle here. And it has mv star, right? And this guy has mv0 equals to 0, right? Then at the end, we have these two guys going together. So that would be mv final, mv final. And what forces act on our system? I think we have mg here. We have mg here. We have some normal force. and some internal forces acting between our two bodies. Yes, so we are not gonna show them at all. Yeah. So again, the forces act only in this direction. Yes, forces act only in this direction. There are no forces in the horizontal direction. Okay, so let's write our, yes, Trevor?
Should the velocity of the wagon in the right picture have a little m via?
Yes. I was testing you, of course. No, I'm kidding. I made a mistake. Okay. Of course, it should be little m, yeah. And probably also, if you really want to be picky, I am sometimes picky, yeah. I should probably write n in here, n in here, and n in here, yeah. N1 and N2, right? Because this will be the reaction forces between that cart and the ground, yeah? But anyway, it doesn't change the solution at all. It doesn't change the solution at all because they're still acting only in this direction, yes? So now momentum equation is following. So we'll write it for the x direction, and which direction I want to be positive. Let me see. This one, why not? This is our positive direction. So we will have big M V star at the beginning plus 0 equal to M plus M V final. And they asked us to find V final. So V final is exactly M plus M V star. Plug in values and obtain that this is approximately 20.721 feet per second. Questions? Okay, guys, we have 3 minutes. Can we do it? I think I can do part B in 3 minutes. Okay? So now we have exactly the same situation. So let's we have exactly the same situation. So let's draw our card 3 times. Our particle, but right now, so our particle again enters here with mv star, and this die has velocity 0. But this time that card is attached here. Okay, there's a constraint here. Okay? And now this die has mv final equals to 0, and this die has mv final equals to 0. So somebody told us to just solve that problem for a different case, right? They told us to solve for exactly the same problem, but with this thing holding our card. And they just ask us to find this value. The impulse of that reaction force. Okay, so let's do our momentum equations. So again, in the x direction, with this direction as positive, we will have mv star plus negative t dt of t0 to tf. Yeah, so I can put that minus here. I can just put that minus here. And this is equal to 0. Because there is no motion at the end, yeah? So let's call it maybe impulse, just to save some ink. We can call this impulse or IMP. So IMP is equal to big M V star. If you plug in values, you will obtain that this is 40 divided by 32.2 times 31.0805. Plug in values and obtain that INP is equal to approximately 38.610 pounds times second. This is our answer. Questions? I think it's already 11:50. So thank you so much for today. If there are some questions, I can stay here for a couple of minutes. See you Friday.